Welcome back to the Calculations in Thermodynamics using John Coley's 7th edition physics textbook. This is part 2. We will spend this PowerPoint looking at the second half of chapter 15 in thermodynamics. Example 15-8 deals with efficiency, and in efficiency you define it as work over the highest level of heat, or the input heat. So in this particular case, your highest level of heat could be defined then as work plus your lowest heat, or heat lost. And since no machine is ever efficient, efficiency can also be defined as 1, being 100% efficiency, minus the proportion of heat lost to heat added. 15-8. An automobile engine has an efficiency of 20% and produces an average of 23 kilojoules of mechanical work per second during operation. A, how much heat input is required, and B, how much heat is discharged as waste from this engine per second. Okay, this is a pretty straightforward problem. Efficiency is work over heat input. Heat input is work over efficiency. Okay. 23,000 joules, or 23 kilojoules of work was provided. The efficiency is 20%, or 0.2, mathematical terms. There are no units for efficiency, so you just plug in. 23,000 over 0.2 provides you with the input energy of 115 kilojoules. Okay. Part B asks how much heat is lost through waste. So if efficiency is 1 over the proportion of heat lost to heat added, the proportion of heat lost to heat added is 1 minus efficiency, rather. So you can rewrite this equation a third time. The heat lost is equal to 1 minus total efficiency times the heat input. The heat input we just calculated was 115 kilojoules times 1 minus 0.2 gives you 0.8, which leaves you with a value of 92 kilojoules of heat lost. That is efficiency. But as we said earlier, no machine is 100% efficient. In fact, the third law of thermodynamics states that no machine could ever be 100% efficient in thermal exchange. Heat engines function on heat exchange, but they don't harness all of it. So heat added or lost is proportional to the temperature added or lost. Using temperature, you can calculate an ideal efficiency based on heat added or heat lost. And your ideal efficiency formula looks like this. So, let's take a look at an example of efficiency. A steam engine operates between operating temperatures of 500 Celsius and 270 degrees Celsius. What is the maximum possible efficiency of this engine? First of all of your temperatures must be in kelvins. 500 degrees Celsius is 773 degrees Kelvin. 270 degrees Celsius is 543 degrees Kelvin. From here, it is a simple rearranging of the formula, plug and play. Your ideal efficiency in this particular case is 0.3. Seen right here. Okay. You can use this ideal efficiency to understand whether or not a manufacturer is making phony claims about a product. An engine manufacturer makes the following claims. An engine's heat input per second is 9 kilojoules at 435 degrees Kelvin. The heat output per second is 4 kilojoules at 285 degrees Kelvin. You can use these 4 separate pieces of information to determine whether or not the manufacturer is being truthful. So based on the heat input and lost, the kilojoules, the amount of energy, the efficiency, is going to be 0.56. Okay, that's a reasonable claim. But what about based on temperature? Well, the ideal efficiency of this particular engine is only 0.34 based on the numbers. These are not equivalent. They do not add up. They're not the same number. Therefore, the Carnot ideal efficiency has been exceeded, and you have violated the second law of thermodynamics, meaning it's not possible. This is a sham. What if we take the idea of efficiency in a machine and equate that to the performance of the machine? Well, look at an ice machine. A freezer has a coefficient of performance of 2.8 and uses 200 watts of power. How long would it take to freeze an ice cube tray that contains 600 grams of water at 0 degrees Celsius? Well, you have to remember that this is a phase change, and it's a phase change from higher energy to lower energy. So in the end, we're losing energy here, kinetic energy. Freezing occurs below the latent heat of fusion for any compound. So what we need is the latent heat of fusion for water, since we're freezing water. Okay. Q is equal to mass of your fluid times the latent heat of fusion. The latent heat of fusion for water is 333 kilojoules per kilogram. So we just plug this in. The heat lost is 0.6, or 600 grams, times 3.33 times 10 to the 5th joules per kilogram. Your resulting heat loss is 2 times 10 to the 5th joules. Now we're going to take that and we're going to plug that in somewhere else. Power is work over time. The unit for power are watts, and if watts are work over time, then watts must be joules over seconds. Therefore, the equation for power must be joules over second. If your freezer uses 200 watts or 200 joules per second, you can use that information to calculate your coefficient of performance of your freezer. And if you can calculate the COP, you can rearrange this formula here to calculate the amount of work being done by the ice machine, the freezer. Work is equal to the heat loss divided by the coefficient of performance. Well, to find time, we rearrange the formulas here, okay, based on power, to determine the coefficient of performance, or to determine the time, rather. Sorry. So work, which is heat lost over COP, is divided by the amount of power. Okay, fair enough. We can rearrange this formula again, though. We can remove this COP and place this on the denominator, as it's a denominator within the numerator placement. So your new formula will look like this. Time is equal to heat lost over coefficient of performance times work being done. Here is your heat loss, here is your coefficient of performance, and here is your power. Therefore, it would take about 6 minutes to freeze that ice tray. All right. What if we're dealing with changing the temperature in an entire room? In this case, we're going to deal with a heat pump. Now, a heat pump can work in two directions. It can either heat up a room, or it can remove heat from a room, much like an air conditioner. So a heat pump has a coefficient of performance of 3.0 and is rated to do work at 1500 watts. A, how much heat can it add to a room per second? B, if the heat pump were turned around to act as an air conditioner in the summer, what would you expect its coefficient of performance to be, assuming everything else was the same? Well, let's identify our variables. Your coefficient of performance is 3. Your work is 1500 joules per second. A, how much heat can be added? And B, what is the coefficient of performance if we reverse the direction of heat flow? Okay. Well, this is a relatively straightforward problem. The formula for heat added is your coefficient of performance times your amount of work. So in this case, it's 3 times 1500, which results in 4500 joules of work per second. Joules of heat, rather. Okay. Now, what if we reverse directions? Now, we're not looking for heat added, we're looking for heat lost. So we need to rearrange the formula for heat added based on work. What results is heat added minus work being done. From here, it's a simple plugging in of variables. We calculated the heat added in the last equation, part A, and now we're going to use that to find the heat lost per second in this particular, the coefficient of performance in a minute. Okay, our heat lost is 3000 joules. the formula for coefficient of performance is heat lost over work. Now, in this particular case, the heat lost is 3,000 joules. The work being done is 1,500 joules, so your coefficient of performance for this particular air conditioning unit is 2.0. When we're dealing with thermodynamics, you have to keep in mind the kinetic energy theorem. You have to keep in mind the idea that heat is energy and energy causes entropy. So when you are heating up or melting a solid, you are increasing the disarray in the molecules, increasing entropy, and vice versa when freezing them. So an ice cube of mass 56 grams is taken from storage at 0 degrees C and placed in a paper cup. After a few minutes, exactly half of the mass of the ice cube has melted, becoming water at 0 degrees Celsius. Find the change in entropy of the ice water. Well, entropy is denoted as delta S. It's always a change. Okay? And S equals change in heat over T. Your change in heat here, or your heat added or heat lost, is equal to mass times the latent heat of either vaporization or fusion of your fluid. In this particular case, because we're melting ice, it's going to be the latent heat of fusion, and the latent heat of fusion of water is 333 kilojoules per kilogram. Now, you may have noticed that this says 0.028 kilograms as opposed to 56 grams. Well, 56 grams is twice as much as 0.028 kilograms. 0.028 kilograms is half the mass of the ice cube that's melted. Multiplying these two numbers results in your Q value, which is going to be 9.3. Okay, now, the temperature at 0 degrees Celsius is 273 degrees Kelvin. So in that particular case, this is a simple, straightforward example. The change in entropy is equal to your energy divided by your temperature. 9.3 over 273 results in 34 joules per Kelvin. Again, remember, this is kilojoules, not joules. Okay. So what if we started mixing fluids at different temperatures? Would the entropy change between water samples? Well, we have two samples of water, both weighing 50 kilograms, with two different temperatures of 20 degrees Celsius and 24 degrees Celsius. Imagine the change in entropy. Q is equal to mass times your specific heat times your change in temperature. Okay. Well, in this particular case, 50 kilograms of water at this specific heat times your change in temperature results in this much energy. Q will remain static in water due to water in both cases. So Q is not going to change. All right. So in this particular case, we will use average temperatures for hot and cold water, and those temperatures will be in kelvins. We will find the specific entropic change for each water temperature, and then we will combine for the final entropic difference. We're going to use this formula here. Let's get to it. Okay, the entropic change for the hot water is going to be 1,414 joules per Kelvin. The entropic change for the cold water is going to be 1,424 joules per Kelvin. The total change in average entropy, based on these calculations, is 10 joules per Kelvin. Now, let's go back for a second. Here is your Q value. Delta S is Q over T. Here's your temperature. Here is your Q. Here is your S value for the hot water. Here's your Q. Here's your T. Here's your S value for the cold water. Now we're averaging those two changes in temperature together, acting like a net force, doing a simple calculation, and calculating the final change in energy. I hope that this has been enlightening. I will work on the next chapter as soon as I possibly can. Thank you very much for joining, and subscribe if you find these videos useful.